welcome to the deep dive. If you were following the world of large language models at the start of 2025, you're probably still asking that same old question. Is it just mimicking, or is it actually thinking?
Yeah, that was the big debate.
Well, by the end of the year, that question was pretty much settled. 2025 was the year we stopped just talking about AI reasoning, and, well, we saw it emerge as a tangible, scalable technology, and frankly, it was shocking.
It really wasn't a gradual thing, not at all. It was a fundamental architectural shift.
Right.
Suddenly, these reasoning capabilities, which we all thought were years away, became a core feature that companies could, predictably optimize for.
Exactly. And we have a massive stack of sources in front of us. Lab reports, technical breakdowns, critiques, safety analyses. Our mission today is to give you the shortcut to understanding the huge paradigm changes of 2025.
Hmm.
We're going to dive into the technical breakthroughs that unlocked it all, explore how we've had to completely rethink what AI intelligence actually is, and then tackle the urgent and often contradictory state of AI safety.
And what really stands out when you look at all this is this central tension. One researcher put it perfectly. He said these LLMs are a lot smarter than I expected and a lot dumber than I expected.
Right.
They can solve a problem a PhD would struggle with, but then get tripped up by, grade school logic. But the consensus is clear. The field is wide open. We're nowhere near even 10% of the potential that's just been unlocked.
Okay, so let's unpack that. Let's start with the technical engine that drove this whole thing. Reinforcement learning from verifiable rewards.
Right, but first we need to set the scene. For the longest time, the recipe for building a powerful LLM was very stable. It had three proven steps.
The old stack.
The old stack. First, pre-training on mountains of data. Second, supervised fine-tuning SFT with high-quality examples. And third, that very short stage of reinforcement learning from human feedback, RLHF.
Which was basically just to make it polite and helpful.
Exactly. But then 2025 brought in what is now the de facto new stage, the one that broke the mold, RLVR, reinforcement learning from verifiable rewards. This is the thing that gave us scalable thinking.
So what's the core difference?
It's all in the reward function. RLHF asks a model to optimize against, messy human preferences. It's like grading an essay on how nice it sounds.
Subjective.
Totally objective. RLVR just ditches that entirely. It optimizes the model against objective, non-gameable reward functions.
So instead of being judged on politeness, it's judged on results, like complex coding challenges or math proofs where the answer is just definitively right or wrong.
Precisely. The outcome is binary. It's verifiable. And this is crucial. RLVR involves training for a much longer period than that thin RLHF stage. You're not just polishing the surface anymore. You're fundamentally changing the gears inside.
You're letting it chew on thousands of these hard problems.
Hundreds of thousands. And what happened?
What did happen?
This is where it gets really interesting. The LLMs, under this intense objective pressure, spontaneously developed these complex, human-like strategies that look exactly like reasoning.
Like what? What kind of strategies?
They learn how to break down a problem into intermediate steps. They learn to backtrack when they hit a dead end, and they learn really complex self-correction.
Well, how could they prove that? I mean, how did they know it was learning a strategy and not just getting better at pattern matching?
The DeepSeek R1 paper had some great examples. They could actually trace the model's internal steps and see it adopting these methodologies. Like, it would realize a direct calculation failed and then recursively try a different approach.
Wow.
It was proof of internalized strategy, and the inflection point for all of us was, I think, the OpenAI O3 release in early 2025. Suddenly, the whole thing just felt different, more grounded.
That makes sense.
Yeah.
But building and retraining these massive models is still astronomically expensive.
Yeah.
So did this reasoning breakthrough give the labs a way to improve capabilities without having to sink billions into pre-training every few months?
Absolutely. The ability to reason led to the discovery of a second huge dimension for scaling, inference time compute. This is now one of the highest capability games you can buy per dollar.
Wait, let me make sure I'm getting this. You're saying we can get dramatically better results just by paying for the model to think longer after the user hits send?
Mm-hmm.
Without more training?
Yes. It's not cheating, it's just optimizing for this new capacity for serial thought. The old goal was just to generate the final answer. Now you realize that generating longer reasoning traces before the final answer, that thinking time, vastly improves the quality. That's the new inference time scaling law.
So how does this actually show up for a user?
Look at Claude 3.7 Sonnet. It literally gives you a toggle for an extended thinking mode.
I saw that.
When you switch it on, the model expends more effort. It's using what we call serial test time compute, and the performance gain is predictable. Sources show accuracy on hard math questions improves logarithmically with the number of thinking tokens it uses.
You pay a bit more compute, you get a much better answer. So that's serial. But I also saw some research on parallel test time compute. That seems even more aggressive.
It is. In the research previews, they are running multiple independent thought processes at the same time.
Like asking 5 different AI brains the same question.
Pretty much. Then they pick the best answer using a majority vote or a learned scoring function. This got them truly striking improvements on benchmarks like GPQA, which is graduate-level science knowledge. It hit 84.8%.
It's like an instant supercommittee.
Right.
And one of the most fascinating things to come out of this was Anthropic's decision to make the whole thought process visible in Claude 3.7. Why would they take that risk?
The intention was, transparency and trust. If you can see the step-by-step reasoning, it helps with alignment checking. If the final output is deceptive, you can sometimes spot the contradiction in its internal monologue versus its final action.
And it's just cool to watch.
And it's just cool to watch, let's be honest.
But I've got to assume that level of transparency created some massive security issues right away.
Oh, absolutely. It's a classic trade-off. Bad actors immediately start using that visible process to reverse engineer better jailbreaks. If you can see how the AI is thinking, you can find the chinks in its armor much faster.
Which means the labs are probably already talking about fighting those thoughts in the future.
Immediately, the discussion turned to whether future, more capable models might need to encrypt or, hide harmful internal thoughts because transparency is just too exploitable.
That technical focus on how the models reason brings us perfectly to the big conceptual shift of 2025. We have to stop thinking of these things as digital versions of ourselves, as animals, and realize we're actually summoning ghosts.
That analogy is so important. Our intelligence, our animal brain, evolved under one massive optimization pressure.
Right.
Survival.
Right. Don't get eaten.
Exactly. LLMs are optimized for imitating text and, now, for collecting rewards in math puzzles. The optimization pressure is fundamentally different. The ghost exists only in a digital world of text and logic, not the physical world of, gravity and social survival.
Which leads to this idea researchers started calling jagged intelligence.
Yes, the LLM is simultaneously a genius polymath and a confused and cognitively challenged grade schooler. It's brilliant, but its capabilities are incredibly patchy.
They spike. They have these enormous peaks, or jaggies, in the specific domains where you can apply those objective, verifiable rewards from RLVR.
Precisely, like coding or formalized math.
And this is why we saw so much apathy and loss of trust in the traditional benchmarks in 2025.
Of course, because benchmarks, by their very nature, are verifiable environments. They became immediately susceptible to this new optimization trick, what people started calling benchmaxing. Teams just built environments right next to the benchmarks to grow those jaggies on purpose.
I can see why that's frustrating.
Yeah.
But we did see real progress in those narrow domains. What were the big jumps?
Well, look at ARC-AGI-2, the abstract reasoning benchmark. The grand prize is still unclaimed, but the top model, Opus 4.5, hit 37.6%, and some specialized solutions pushed that over 50%. We also saw huge breakthroughs in IMO Gold for math and models, hitting 100% on the ICPC coding competition. Those are genuine leaps.
But if you know the benchmark is being gamed, you have to change the game.
And they are. The people behind the ARC prize know this. So the next version, ARC-AGI-3, is releasing in early 2026, and it's introducing a major format change. It's designed to challenge interactive reasoning.
So it's not enough to just give a perfect answer anymore?
No. The AI has to demonstrate skills like exploration, planning, memory, even goal acquisition, all inside an interactive world.
And for the first time, they're formally comparing human versus AI action efficiency, right?
Right.
Not just if it solved it, but how much work it took. That feels huge.
It connects right back to that ghost analogy. The foundation model is the brilliant but aimless college student. Now we need to turn that student into a deployed professional.
Which brings us to the new app layer.
Yes, the new innovations in deployment and interface. Apps like Cursor, the AI coding editor, convincingly showed us this critical new layer.
The LLM app layer.
Right. These apps are doing the heavy lifting the foundation models don't. They handle context engineering, they orchestrate multiple LLM calls into complex graphs, and they provide specific EUIs.
So the lab produces the brain, but the app layer organizes it. It gives it private data, sensors, actuators.
Yeah.
It gives the ghost a profession.
Exactly. And this led to a new paradigm. the
Yeah.
local agent. We saw the breakthrough with Claude Code, or CC. It was the first truly convincing LLM agent that could string together tool use and reasoning for, long, complex tasks. It was stable. It was useful.
And the key distinction was that it runs on the user's local host. Why is that so important?
Because it runs with your private environment, your data, your context, it acts as a little spirit that lives on your computer.
Instead of in the cloud.
Yes. All the earlier ambitious agent efforts were cloud deployed, which created huge security and latency problems. The local host agent just solves those trust issues immediately.
And as we started interacting with these local spirits, the interface began to change too. We finally realized that the basic chatting interface is just wildly inefficient.
It's the digital equivalent of a command line from the 1980s. Text is easy for the computer, but people process information visually and spatially. We're much faster with images and infographics than walls of text.
And that's where Google's Gemini Nano Banana came in, hinting at this necessary LLM GUI, a graphical user interface.
The notable part wasn't just that it could make images. It was the joint capability. Text generation, image generation, and world knowledge all tangled together in the same weights.
So it wasn't just generating an answer and then prompting an image tool.
No, it was communicating its knowledge in your preferred visual format. It could create a diagram or a slide as its primary output. It was communicating visually.
All of this progress just put the whole AGI timelines debate into overdrive this year. What's the state of that conversation?
Well, there's still no shared definition of AGI, which makes it hard. But the timelines are wildly divergent. OpenAI is still targeting a breakthrough before 2030, based mostly on an economic definition.
Okay.
DeepMind is more scientifically focused, looking toward the early 2030s.
And then you have Anthropic projecting powerful AI by 2026, while Meta is way more cautious, saying it could be years or even decades away.
And it's worth noting, historically, experts have always predicted AGI is about 15 to 25 years away whenever you ask them. But the rate of progress now is, well, it's unprecedented, even if the models still lack real-world common sense.
As the timelines shrink, the urgency around safety governance just skyrockets. And a really novel approach emerged this year, the Language-Mediated Active Inference Framework, or AIF.
Right. This is about building inherently safer AGI, moving beyond just testing it after the fact.
How does that work?
AIF basically tries to embed safety into the core decision-making process. It's neuroscience-inspired. The agent is always acting to minimize its own uncertainty while fulfilling its goals, so it's constantly balancing curiosity, what they call exploration, with fulfilling the specific constraints we set, which they call preferences.
And then the LLM itself is the medium for all of this.
Exactly. Language is used to represent and manipulate the agent's internal model and its beliefs. It makes it much more transparent. Safety constraints, like don't be deceptive, are encoded as these core preferences that govern its actions. It's a structured way of steering the AI.
But a framework like that has to have risks. What are the dangers?
Two big ones. First, computational complexity. Natural language reasoning creates a combinatorial explosion. It's just very, very hard to track. Second is the risk of language games.
What's that?
The model could learn to generate perfect, safe-sounding answers about its beliefs without actually grounding those beliefs in safe behavior. It might learn to lie about its internal state simply to satisfy the preference of sounding safe.
So we needed a reality check. And the 2025 Frontier AI Trends Report really delivered one. It grounds all this theory in hard data.
And the capability surge they describe is genuinely alarming. Models now significantly outperform PhD-level experts in open-ended chemistry and biology questions. They're surpassing the expert baseline by 60%.
So they're already capable of scientific discovery beyond human capacity.
In some domains, yes. And the cybersecurity results were just as stunning. Models went from apprentice level in 2023 to completing expert level tasks that need 10+ years of human experience in 2025. Autonomy on hour-long software tasks shot up from less than 5% to over 40%.
That's a staggering jump.
And while the safeguards are getting better, some models require 40 times more effort to find a jailbreak. That progress is really patchy. It's uneven.
And this is where the most critical, most alarming finding from that report comes in. The safeguard disconnect. They measured capability against safeguard robustness. Was the correlation?
Minimal. I mean, almost no statistical connection. The R-squared value was a meager 0.097.
Which, in plain English, means what?
It means they found less than a 10% correlation between how smart a model is and how hard it is to attack.
Wow. So a smarter model is not a safer model.
Not inherently, no. In fact, if the defenses aren't dramatically improved, A smarter system may actually be easier to attack. The smarter the core model, the more ways a subtle attacker can get around a weaker monitoring model, maybe by using a language or encoding the defense doesn't recognize. The risk is shifting fast.
So the core tension of 2025 is just
Yeah,
stark.
yeah.
We unlocked scalable reasoning, which is fueling these incredible leaps in science. But this jagged, ghost-like intelligence presents these immediate, profound challenges in safety and control.
We're moving faster than we ever thought possible, but we're still in the very, very early stages of understanding what we've actually created. It's a moment of total intellectual whiplash.
Which leaves us with a final, provocative thought for you to chew on. The history of AI has something called more of X paradox. It states that tasks that are easy for humans, sensory-motor skills, common sense, loading a dishwasher, are computationally much harder for an AI than abstract reasoning tasks, like solving PhD-level math.
Right, we've just spent 2025 watching AI absolutely crush those hard, abstract reasoning tasks.
So if Moravec was right, and we've just unlocked the easy half of AI with these new reasoning models, what does that truly mean for our expectations when the problems we still haven't solved, the things that we take for granted every single day, like robust common sense and physical dexterity, are, by this paradox, the truly difficult ones still ahead of us?
Something to think about.